Hello, my name is Laurel Robinson. I'm a professor here in the Physical Sciences Department at WCC. I'm not physically here with you today because I've traveled to Texas for optimal eclipse viewing. However, I wanted to leave you with some information about today's eclipse to help you put into context what you are seeing. I'm going to start off by telling you exactly what a solar eclipse is and what causes them. We will then talk about how often they happen and specifically what you can expect to see today. We will end with talking a little bit about solar eclipses from a scientist's perspective. What can scientists learn from studying solar eclipses? And lastly, before we start, here's a picture of me and my husband. That way you can put a face to the voice talking to you. If you see me on campus, please say hi. Solar eclipses have occurred since the beginning of the Earth. However, the first evidence we have of one being recorded in human history is from rock carvings in Ireland. These carvings are dated from around 3300 BC and are thought to depict a solar eclipse. The big circle is thought to be the eclipsed sun, and the smaller surrounding circles are thought to be stars that suddenly became visible in the dark sky of the eclipse. Immediately in front of this carving, archaeologists found the charred remains of nearly 50 individuals. It is interesting to speculate what the connection might be and what these ancient peoples may have thought of the solar eclipse. Since then, there have been many other mentions of solar eclipses in history. I'll highlight some of the interesting ones. Around 1200 BC, scribes in China recorded an eclipse on oxen's shoulder blades and tortoise shells. In their records, the scribes wrote, "The sun has been eaten." In the Quran, a solar eclipse is mentioned before the birth of Muhammad. The Mayans in Central America were skilled astronomers, and their records predict solar eclipses hundreds of years in the future. At Chaco Canyon in New Mexico, the early Pueblo people carved the drawing of an eclipse shown here. It is thought to represent an eclipse that occurred on July 11th, 1097. Lastly, King Henry I of England died shortly after an eclipse in 1133. This prompted a widespread superstition that eclipses are bad omens for rulers. While ancient peoples might not have had the scientific knowledge to put what they are seeing into context, we today are fortunate to know exactly what causes a solar eclipse. This image shows a side view of the Earth-Moon-Sun system during a solar eclipse. A solar eclipse occurs when the moon blocks the light from the sun and casts a shadow onto the Earth. Notice there are two parts to the shadow that is cast by the moon. The umbra is the inner cone-shaped part of the shadow. It is on the order of 100 miles wide and is where the light from the sun is completely blocked. The penumbra is the outer part of the moon's shadow. It is where the light is only partially blocked. Here is what this looks like on the Earth. This shows a moment during the solar eclipse of August 21st, 2017. Locations that are within the umbra will see a full total solar eclipse, i.e. the entire sun will be blocked, and locations in the penumbra will see only a partial solar eclipse, i.e. only a part of the sun will be blocked. As the Earth rotates, the umbra and the penumbra will move across the Earth. The diagram here shows the path for today's eclipse. Locations in the path of the total solar eclipse are completely in the umbra, and the closer you are to this path, the greater the partial eclipse you will see. The maximum extent of the eclipse is determined by the sunrise and sunset lines. So, for example, if you are located in Europe, you're not going to see the eclipse because the sun will have set already by the time the eclipse occurs. Before we move on, the teacher in me needs to go back and clarify something, and that is that this diagram I showed you before is not to scale. In fact, the distances between the sun, the earth, and the moon are so far, and the sun is so large in comparison to everything else, that it is not actually possible to give you an accurate picture on a PowerPoint slide. I can, however, describe an accurate scale model to you. If we represent the sun as a basketball at the 0-yard line of a football field, the Earth would be a large grain of sand placed at about 37 yards. The moon would be a much smaller grain of sand orbiting the large grain of sand at a distance of roughly 3.5 inches away. So hopefully this gives you some better sense of perspective here. There are actually 3 kinds of solar eclipses. We already mentioned a total solar eclipse, which is when the moon entirely covers the sun. We also already mentioned a partial solar eclipse, which is when the moon only partially covers the sun. There is also an annular eclipse. Here, the moon is entirely in front of the sun, but some of the sun's edges are still visible. It turns out that the moon's orbit around the Earth is not a perfect circle. It is in fact slightly oval. Thus, the moon will be slightly bigger or smaller in the sky, depending upon its current distance. This will determine whether you get an annular or a total solar eclipse. Here's an example of an annular solar eclipse. This is also called a ring of fire eclipse because the sun literally looks like a burning ring of fire. Here's a time-lapsed photo of a total solar eclipse. The moon gradually covers greater and greater portions of the sun until the point of totality. At the point of totality, the sun and the moon are the same size in the sky, so the moon entirely covers the sun. The glow around the moon is the sun's outer atmospheric layers called the corona. The corona is usually not visible because the sun is too bright. It is only during a total solar eclipse that we can actually see it. After the point of totality, the moon will gradually move away from the sun. It is actually a pretty crazy coincidence that the sun and the moon are the same size in our sky, since in actuality the sun is about 400 times larger in width than the moon. If this were not true, a solar eclipse would not be quite as stunning. For example, here is an eclipse as viewed from the surface of Mars. This eclipse was recorded by the Curiosity rover and shows the Martian moon Phobos eclipsing the sun. As a fun thought experiment, let's imagine that you were an astronaut in space looking back at the Earth during a total solar eclipse. What would the eclipse look like to you then? Here's an image that was taken by NASA's Deep Space Climate Observatory spacecraft in 2016 that shows you. The dark blob in the middle of the Earth is the moon's shadow. Here's some terminology you may hear today. First contact is when the moon first starts to pass in front of the sun. Second contact is when the moon first starts to completely cover the sun and is the start of the total solar eclipse. This is also sometimes called the diamond ring phase because the sun looks like a diamond ring. Third contact is when the total solar eclipse ends, and fourth contact is when the partial solar eclipse ends. You might now be wondering why we don't have eclipses every month, since the moon orbits the Earth once a month. The answer is that the moon's orbit is tilted about 5 degrees relative to the Earth's orbit around the sun. In this diagram, the Earth's orbital plane around the sun is shown by the red line, and the moon's orbit is shown by the white oval. This means that generally the moon's shadow is going to fall either above or below the Earth and will not create an eclipse. In fact, there are only 2 times each year when the orbital planes are aligned. So this means there are only 2 times each year when the shadows have the potential to be aligned and there is a chance for an eclipse. If the moon is in the full moon phase during that time, you will have a lunar eclipse. If the moon is in the new moon phase during that time, you will have a solar eclipse. It will be either an annular or total, depending on the moon's current distance. This map shows total and annular solar eclipses in the continental U.S. from 2001 to 2050. Total eclipses are shown in blue, annular in yellow. There was a total eclipse back in 2017 that ran from west coast to east coast. You may remember this one. Today's eclipse runs from Maine and down all the way through Texas. The next eclipse will not be for another 20 years. There's one in 2044 that just barely hits the northern U.S., and one in 2045 that runs from California all the way through Florida, incidentally including Disney World. The next time a total solar eclipse will be visible from New York is not until May 1st, 2079. During this eclipse, Valhalla will actually be in the path of totality. Here's a close-up of the path of today's eclipse in New York. If you happen to be watching this video from Syracuse, Rochester, Buffalo, or other parts of northwestern New York, you are in luck and will see the full total solar eclipse. Other parts of New York will see a partial solar eclipse. This diagram shows what our area will experience. The totality line is the red line at the top of the page. Locations closer to this line will show greater partial eclipses. In Westchester, we will see about 90% eclipse, which means that the sun will dim by about 90%. This sounds like a lot, but it will still actually appear like daylight bright to your eyes. This diagram shows what we can expect to see here in Valhalla. The eclipse will begin at around 2:10 p.m. The moon will gradually cover more and more of the sun until it reaches maximum eclipse at around 3:25 p.m. The moon will then gradually move out from in front of the sun, with the eclipse ending around 4:40 p.m. So it will last for a total of about 2.5 hours. There's one key point to safely viewing the eclipse, and that is to not look at the sun directly, as doing so can damage your retinas permanently. The exception is if you are in the path of totality. During totality, and during totality alone, it is safe to look at the sun directly. Otherwise, you should use your eclipse glasses or make a pinhole projector. To do this, place a small pin-sized hole in a piece of cardboard and hold this over a sheet of white paper with your back to the sun. The hole will act like a tiny camera and will project an image of the eclipsed sun onto the paper. Solar eclipses are unique opportunities for scientists. I'll give you 2 examples. First, let's look at a diagram of the sun's layers. At the center is the core, where nuclear fusion releases energy. This energy is brought to the surface through the radiative and convective zones. The photosphere is the part of the sun that we see from Earth, and then there are several outer atmospheric layers ending in the corona. The corona is the sun's outermost atmospheric layer. Normally, we can't see it. However, during a total solar eclipse, the rest of the sun's light is blocked, and the corona becomes visible, with eerie streams of glow streaking across the entire sky. Scientists have used solar eclipses to study the properties and structure of this layer. As another example, let's turn to Einstein's theory of general relativity, proposed in 1916. This theory says that objects with mass warp space-time. We can visualize this if we imagine space-time as a tautly held sheet and then place a marble on it. The marble will warp the surface of the sheet. A bigger object, like a bowling ball, would warp it more, just like more massive objects warp space-time more. Objects attempting to move in a straight path past the massive object will be affected by this warped space-time and end up moving in a deflected, curved path, like the red line shown here. This includes light. Light moving past a massive object in space should be bent due to the distorted space-time around the massive object. Einstein described how, according to the general theory of relativity, light traveling past the sun should be bent by a measurable amount. Unfortunately, he was unable to test this because the sun is so bright, it makes it impossible to see stars near it. However, in 1919, scientists were able to conduct the first test on the general theory of relativity by measuring the light from stars visible during a total solar eclipse, supporting Einstein's theory. This concludes the presentation. Please enjoy the eclipse, everyone.